We got a good one for you today. I want to learn about logistic growth. Got 2 days of it. So today's video notes is really just more of a understanding what it is, and then the next days is more of a algebraic version of it, solving for it, stuff like that. So let's talk about what a logistic growth is. Before I get to that, let's just remind you of a couple things on some other graphs. So what I'm sketching right now in this magenta color is an exponential. So as it goes, as it increases to the right, the value increases a lot, and it keeps increasing. And then in blue here, I'm going to draw logarithmic. So this is a log graph. And if you notice, this one increases as we increase to the right, it gets slower and slower and slower. So a logistic is actually the in-between of these two. So a logistic, which I'll sketch here in black, looks like this. So it's a bit of the exponential, and then starts to slow down, and then it starts to look like a log. And then here we have asymptotes on the top and bottom. Now, a logistic curve is more of a realistic way to predict populations, because if you remember back in pre-AP pre-calculus or Algebra 2 even, we get some questions about populations like increasing, like if the population of bunnies doubles, then how many will there be in 60 years? Well, the problem with that is it can't keep doubling forever and ever and ever, because eventually we'll run out of surface area on this earth, and that'll be it for the bunnies and everybody else. So a logistic curve, what it does is it kind of limits the capacity of the population. So I'm kind of read here. I kind of talked through most of this already. So situations, population growth levels off and approaches a limiting number because of the limited resources. In the situation of the rate increase or decrease is directly proportional to both L and L minus P. This is called a logistic growth, and it's modeled by this differential equation. So logistic growth is from this equation right here. L is going to stand for the limiting capacity. Okay, so that's what L is. So that is the limiting capacity. And then P is just going to be the population. All right, so this is just saying that the change in population is going to be equal to K times P, which is population, and then limiting capacity minus population. Okay, so we're going to go through. Sometimes we're given logistic equations that look just like this, and it's super easy to kind of pick everything off. Sometimes they look a little bit different. We have to do just a little bit of math to make it look like this form right here. That way we can play around with it. And if you take the derivative of this, which is the second derivative of P, of the population, we can find out more important facts about when P is growing the fastest. Okay, so let's do example number 1 here. So the entire front pages. So the population, P of T of fish, so P is the population of fish, and it satisfies the logistic differential equation, and it shows us this right here, where T is measured in years, and the initial, so P of 0 equals 4,000. This is the initial, because at 0 years we are at 4,000. Okay, so does this look like a logistic equation? It says it is. Just super nice. They didn't have to tell us that. They said it is. So what I'm going to do is I have to rewrite this so that I can get this L minus P. So I need this P to be by itself. So I need to take out a GCF of P over 6,000, so that this way this becomes just a P right here. So if I were to solve for this now, take out a GCF of P over 6,000. Okay. That's going to give me, well, I'll take out P of the first one, and then so since I'm dividing out 6,000, the opposite operation would be multiplying. So this becomes 18,000. And if you don't believe me, just distribute it, and you will actually get that 3P minus P. So there we go. I'm going to just rewrite this so it looks, so I can easily tell what the K value is. It's 1 over 6,000. Kind of wrote that weird. P 18,000 minus P. So this is clearly my logistic equation, and let's kind of go through this. So this is asking for my end behavior to the right. Now don't forget that I'm going to end up having asymptotes on top and at bottom. So the top one is my asymptote on top. So that's where I'm going to top asymptotes, the asymptote on top. That's my limiting capacity. So essentially, what's the largest number that the population can be? Which is going to be 18,000. Okay. What is the range? So essentially, the range is from, hey, the bottom asymptote to the top asymptote. Well, the bottom, it started at 4,000. Okay. And that's going to go from P all the way up to 18,000. Okay. So it can equal 4,000 because it goes up to that, and it can actually equal 18,000 as well. For values of P, is the solution curve increasing, decreasing? Let's justify our answer. So how do we find out if something's increasing or even decreasing? We got to set the derivative equal to 0 and use the sign chart. So we got to set dp dt equal to 0 and make a sign chart. So let's go ahead and do that. So I'm going to do this in purple. I'm going to set this dB dt equal to 0. So I'm going to get 1 over 6,000 P, 18,000 minus P, set that equal to 0. I'm going to go ahead and do that. Well, that 6,000 just kind of go away because I multiply both sides by 6,000. So I'm going to get P, and I'm going to get 18 minus P equals 0. So as you can see here, I'm going to get P values of 0 and 18,000, but that's 0 is not my range, so I'm not going to worry about that. So my critical values for dP dt, well, my endpoints are 4,000 because I said that, and it's 18,000. Okay. My critical values are at 18,000, and that's already on my graph because it's an endpoint. Other critical point is a 0, but that's not in my range, so I discount that. So now I just got to figure out if it's increasing or decreasing. So just plug in any value in between and plug it in here. So let's just plug in a 5,000. So I'm going to get positive times positive, which is positive. So it is increasing from 4,000 to 18,000. Yeah, you could put brackets on that. It's not going to matter one way or another. It's increasing from 4,000 to 18,000. Why? Because dP dt is positive. And there you go. So it's not decreasing, it's increasing only. Hey, let's find the concavity now because it's asking when is it concave up, concave down. So this is when I find the second derivative. So actually I need to do just a little bit of the work here to find the second derivative. Let's see what I did in my notes here. Okay, good. That's what I thought. So you can take the derivative of it right here. But that's going to involve product rule. Why don't I just take the derivative of the thing that I did before I factored? So I'm going to take the derivative of this form right here just because it's much easier. So I'm going to show that work right here. So second derivative of P with respect to time again equal to, so the derivative right here is just going to be 3 minus, and then this is going to give me 2P over 6,000. Just double checking my work here. Oh, and this is with respect to T. This is, I knew I was doing something wrong. This is actually dP dt. So this is dP dt. This is dP dt. Okay, so I'll write this nicer now. So 3 dP dt minus 2P over 6,000 dP dt. Okay, and I'm going to go ahead and clean this up just a little bit. So this is going to equal, looks like I can take out a dP dt. This is going to give me 3 minus, P over 3,000. I'm going to set this equal to 0. So I'm going to go ahead and have to find my critical point. So I'm going to set this equal to 0. Well, for dBdt, I already did that. My critical points were just at 0 and 18,000, and that's on my endpoints, and the 0 is not in there, so that's not a big deal. So I need to find out my other critical point by setting this equal to 0, and you're actually going to get p to equal 9,000. We can set that equal to 0. So let's go ahead and make our lovely little sign chart. So my range is from 4,000 all the way to 18,000. And then looks like right here, 9,000. Okay. So this is going to be, if you plug in like a 5,000, you're going to get a negative. Oh, no, wait, no, I can't do math. I really can't do math. No, yeah, you're going to get negative. No, getting positive. Okay, I'll actually do the work. So plug in a 5,000, you're going to get 3 minus 5,000 over 3,000. And then this is when you plug in a 5,000 into here. I said it was always positive. What the heck is going on? I know I'm making some mistake that someone's like probably yelling at me like, "Hey, you idiot! It's this." Oh no, it is positive. I am an idiot. 3 minus a number that's clearly smaller than 3. That's positive. Jeez, my bad. And then plug in a number that's bigger than 9,000, like 10,000. So if you plug in a 10,000, you're going to get 3 minus a number bigger than 3, which is negative. dPdt is always positive, so you're going to get negative right there. So here we go. So when is this concave up? So it's concave up from 4,000 to 9,000 because the second derivative is positive, and it's concave down from 9,000 to 18,000 because second derivative is negative. All right, that's like the worst. That says negative, just negative. There you go. I just justified my answers. So when does the solution have an inflection point? So it changes concavity at 9,000. So it's going to be at when p is 9,000, because the second derivative changes signs. I can't spell. Sings. Changes, sings, note signs. And then just wants you to sketch this. So let's go ahead and sketch this. So it says here that my lowest value is 4,000. So that's 4,000. My highest value here is 18,000. Just put that over here because I'm out of room. And so what's going to end up happening here is I'm starting here. And I'm going to end up like this. Okay. And it's going to change concavity right about there, which is at 9,000. Which you want a bit of a hint. It changes concavity halfway through the limiting capacity. Okay. So that's what's going on. So if our limiting capacity is, since it's 18,000, it's going to change concavity at 9,000. If the limiting capacity was like 22, it would change concavity at 11. Okay, so there you go. There's dipping your toe a little bit there into the logistic growth type of deal here. Let's go ahead and do 2 more examples. I'm not going to go as slow because we kind of get the idea now. So this is the same problem, but my initial value is going to start at 10,000. So real quick, I'm just going to rewrite this. dBdt is equal to 1 over 6,000 p, and this is going to be 18,000 minus p. Okay, so limiting capacity, it's the same problem, just a different initial point right there. So I'm going to go all the way out to infinity. Limiting capacity is going to be still 18,000. That did not change. The range now, the range changed. It's going to be from 10,000 all the way until 18,000. I guess I don't really need the equals to there. Why can't? Don't need the equals to there. And I think the same thing on this one. That shouldn't be equals to. That should be just a plain old, because it can't actually equal 18,000. My bad. So that one should just be just a not an equals to, but this one can equal it because, well, it does touch it. Okay, so it's pretty much the exact same work that I have on the previous page. The only difference is that on my sign charts here, instead of it being 4,000, I'm going to be at 10,000. So yeah, so it's the same thing here. It's going to be increasing from 10,000. So it's increasing from 10,000 until 18,000 because the first derivative is positive. And remember, this is the same exact problem that we just did. That's why I'm not showing as much work. The only thing that has changed there is the initial value. When is it concave up? Concave down. Now this is where it's going to change a little bit. Remember that our other sign chart we did, we had a change at 9,000. Well, 9,000 is out of my range now. So this is going to change a little bit. My old sign chart, I had a plus and a minus, but now I'm just going to have a minus because I had 9,000 as a critical value. 9,000 is not in here. So this is only concave down. So it's concave down from 10,000 to 18,000. Why? Because dp, well, d squared p dt squared is negative. Okay, so does this have an inflection point? No. Why? Because the second derivative does not change signs. Okay, so for my sketch, again, my liquid capacity here is here at 18,000. I'm just starting at 10,000 though. So right here is 10,000. So it looks like that. Because my initial value was 10,000. In terms of the bottom asymptote, that was always going to be here at 0, which I feel like I made a boo-boo over here. This asymptote for this one right here, this is why I use pencil, not marker. I'm going to have to use marker because you can't see it otherwise. This asymptote really should be down here, by the way. There should be no asymptote right there, and it says 409 and 4,000. Okay, so for asymptote should be all the way down there. Just give you a heads up. So this is the graph whenever my starting population is beyond the inflection point. Okay, let's talk about one more situation. Same prompt, everything's the same except for my starting point is actually beyond the limiting capacity. So let's talk about what happens in that situation. So same idea here. We got dp over dt is equal to 1 over 6,000 times p, 18,000 minus p. So as I go out to infinity, my limiting capacity is still 18,000, which means I'm going to start at 20,000, and then I need to get down to 18,000. So let's make this problem just a little bit different, because again, I'm going down. Okay, so my range for this one is going to be, well, 18,000 is my lower value, and 20,000 is my higher value. Okay, so let's see when this solution curve is increasing, decreasing. So if I can show you my old work here for purple, I said that we had a critical point at 18,000. But it didn't matter because it was an endpoint. So I just did this range right here. So kind of the same idea here. Make the same sign chart, except now my lowest value is 18,000. And my higher value is 20,000. So now when I plug in a number between that, like 19,000, now again, remember, here was a critical point here at 18,000. It is actually going to end up changing signs if I would have kept going, okay? Because if you plug in a 19,000, you're going to get a negative value. So guess what happens here? Because I have a different range, if I plug in a 19,000, it's going to turn into a big old negative. So in this case, I'm decreasing. And I'm decreasing from 18,000 all the way until 20,000. Because first derivative is negative. When is this thing concave up, concave down? Okay, so this is actually going to be, so same idea from the last line chart. Second derivative to 20,000. So this is going to be concave. What was it before? It was negative, so it's going to be concave. Okay, well, let me just write down. It's easier if I just write down what my second derivative was. So this is my second derivative from previously. So it'll be a little bit easier if I can show you that work. So the second derivative was dp dt times 3 minus p over 3,000. Okay, awesome. So now, when I plug in a 19,000, you would want to probably think to yourself, oh, well, this sign chart, it's going to be negative all the way through, so no big deal. Don't forget, my dB/dt is different. So my dB/dt here is negative. If I plug in a 19,000, this is also negative. So what's a negative times a negative? It's going to be positive. So the difference here is my dB/dt, which before was always positive. Since I'm now past that critical point of 18,000, it changes to negative. So in this case, I'm only concave up from 18,000 until 20,000. And this is because the second derivative is positive. So inflection point, same thing over here. I found that was going to be at really at zero. I have a possible inflection point at 0, but that's on the end point, so it's an inflection point. And then this was supposed to be at 9,000. 9,000 is not my range, so no inflection point. Why? Because second derivative does not change signs. Let's go ahead and graph this. So we still have our asymptote here at 18,000. And we're starting here at 20,000. It's decreasing concave up the entire time. So it's just kind of trying to get to that limiting capacity. So those are all of our different situations of our fish in our lake, depending on the initial condition. Looks a little different. So pretty much here are the 3 different graphs. If I can get them all on here at the same time. I'm trying. So here you go. Initial condition is less than the inflection point. This one is bigger than the inflection point, and this one is bigger than my limiting capacity. So there are your situations.